Welcome! In this session, we'll tackle an intriguing problem titled Longer Contiguous Segments of Ones Than Zeros. We'll explore its nuances, discuss potential approaches, and arrive at an efficient solution. Let's dive in. In this problem, we are working with a binary string S, which is composed entirely of the characters 0 and 1. A key concept here is a contiguous segment, which is a substring of S where all characters are identical, either all 0s or all 1s. The length of such a segment is simply the number of characters it contains. The task is to determine if the longest contiguous segment of 1s in the string is strictly longer than the longest contiguous segment of 0s. In other words, if the length of the longest group of 1s exceeds the length of the longest group of 0s, we return true. Otherwise, we return false. The output is a Boolean value that directly answers this question. Let's take a look at the first example. Here, the input string S is 1101. In this string, the longest contiguous segment of 1s is 11, which has a length of 2. The longest contiguous segment of 0s is 0, which has a length of 1. Since 2 is greater than 1, the condition is satisfied, and we return true. This shows how the comparison between the lengths of the segments determines the result. Now consider the second example, where the input string is 111000. In this case, the longest contiguous segment of 1s is 111, with a length of 3. Similarly, the longest contiguous segment of 0s is 000, which also has a length of 3. Since the lengths are equal, the longest segment of 1s is not strictly longer than the longest segment of 0s. Therefore, the output is false. This highlights the importance of the strictly longer requirement. In the third example, the input string is 11010010. Here, the longest contiguous segment of 1s is 11, with a length of 2. On the other hand, the longest contiguous segment of 0s is 000, which has a length of 3. Since 2 is less than 3, the condition is not satisfied, and the result is false. This demonstrates how the comparison works when the longest segment of 0s is longer than the longest segment of 1s. Finally, let's discuss some additional considerations for this problem. Edge cases include strings that contain only 1s or only 0s, such as 11111 or 0000, where the result is straightforward. Another edge case is alternating patterns of 0s and 1s, such as 101010, where the segments are all of equal length. Additionally, strings where the lengths of the longest segments of 1s and 0s are exactly the same require careful handling since the output should be false. Given the constraint that the string's length can be as large as 100,000, it's important to ensure the solution is efficient and runs in linear time, o(n). To solve this problem, one straightforward way is the brute force approach. Here, the idea is to traverse the binary string character by character, identifying and counting the lengths of contiguous segments of 1s and 0s. As you go through the string, you maintain two variables, max_1s and max_0s, which keep track of the longest segment of 1s and 0s encountered so far. Alongside these, you use a counter to count the length of the current segment. When the character switches from 1 to 0 or vice versa, you compare the current segment's length with the respective maximum and update the values as needed. Finally, you return true if the longest segment of 1s is longer than the longest segment of 0s, otherwise return false. This approach ensures that the entire string is traversed only once, giving it a time complexity of O(n). It is also space efficient, requiring only a few variables, so the space complexity is O(1). However, while simple and effective, the brute force method involves explicitly managing and updating multiple variables, which can make the implementation slightly tedious. Now, to make the solution more efficient and elegant, we can use an optimized approach based on key observations about the problem. First, we note that the binary string alternates between segments of 1s and 0s, but we are only interested in the lengths of the longest segments of each. This means we don't need to store all segment lengths or compare every segment explicitly. Instead, we can dynamically update the maximum lengths during a single traversal. The process involves initializing variables max_1s, max_0s, and current_length to 0. As you traverse the string, you track the current character and count the length of the ongoing segment. When the character changes, say, from 1 to 0, you update the maximum for the previous segment, reset the current length, and start counting the new segment. At the end of the traversal, you account for the last segment and perform the final comparison between max_1s and max_0s to determine the result. This streamlined approach eliminates redundant checks and makes the implementation much cleaner. The optimized approach is both time and space efficient. Like the brute force method, its time complexity is O(n), because we only pass through the string once. However, it avoids the cumbersome variable management of the brute force method. The space complexity remains O(1), as only a few variables are used. This approach is particularly appealing because it handles all edge cases, including strings composed entirely of ones or zeros. Comparing the brute force and optimized methods, the latter is cleaner, requiring fewer updates and less manual tracking of segments. An alternative strategy, such as a sliding window approach, could theoretically work, but it is unnecessary here. Since we are not dealing with substrings of fixed lengths, the optimized method is more intuitive. In conclusion, the optimized approach is the best choice due to its simplicity, efficiency, and clarity. It avoids unnecessary overhead while achieving the desired result with minimal computation, making it an ideal solution for this problem. The problem requires us to analyze a binary string, which is composed of only zeros and ones, and determine the longest contiguous segment of ones and zeros. The goal is to identify these segments and compare their lengths to find the maximum one. To solve this, we start by validating the input to ensure it is a non-empty binary string. If the input is invalid, we need to handle it appropriately, whether by returning an error message or following specific program requirements. Once validation is complete, we initialize a few variables. First, max_1s and max_0s are set to 0 to keep track of the maximum segment lengths for ones and zeros. We also use current_char to track the character we are currently processing and set it to the first character of the string. Lastly, we initialize current_length to 1, which will count the length of the current segment as we proceed through the string. Next, we iterate through the binary string, starting from the second character. For each character, if it matches current_char, we increment current_length since we are continuing the same segment. However, if the character differs from current_char, it means the previous segment has ended. At this point, we compare the length of the completed segment, stored in current_length, with the corresponding maximum variable either max_1s or max_zeros, and update it if the current segment is longer. Then, we reset current_char to the new character and start a new segment by setting current_length to 1. After finishing the loop, we perform one final comparison to ensure the last segment is accounted for, as it would not have been processed within the loop. Finally, we return the larger value between max_1s and max_zeros, which represents the maximum length of contiguous segments of ones or zeros. The algorithm is designed to be both time efficient and space efficient. By traversing the string only once, we achieve a time complexity of O(n), where n is the length of the string. This ensures the algorithm scales well even for large inputs. Additionally, memory usage is minimized because we only need a few scalar variables such as max_1s, max_zeros, current_char, and current_length. We do not store all segment lengths, only the maximum ones, which keeps the memory footprint low. The use of current_char and current_length allows us to effectively track segment boundaries without requiring additional data structures. Furthermore, edge cases such as strings composed entirely of zeros, entirely of ones, or even empty strings are naturally handled by this approach. For instance, strings with all identical characters will simply result in one segment being processed, while empty strings can be detected and managed during input validation. To better understand how the algorithm works, let's walk through an example where the input string is s equals 1100111110000000. We begin by initializing max_1s and max_zeros to 0, current_char to 1, the first character, and current_length to 1. As we iterate through the string, we process each character step by step. At index 1, the character is 1, so we increment current_length to 2. At index 2, the character changes to 0, signaling the end of the 1 segment. We update max_1s to 2, reset current_char to 0, and set current underscore length to 1. This process continues, comparing and updating the maximum lengths whenever a segment ends. After processing the entire string, we compare the length of the final segment to ensure it is included. For this input, the longest segment is 6 consecutive zeros, so the output is 6. When analyzing the complexity of the algorithm, we see that the time complexity is O(n), because we traverse the string only once, making it highly efficient. The space complexity is O(1), as we only use a few scalar variables without any additional data structures. This makes the algorithm suitable for large input sizes. Considering edge cases, the algorithm handles various scenarios seamlessly. For a string of all ones, such as 111111, the output is simply the length of the string, as there are no zeros. Similarly, for a string of all zeros, like 00000, the result is the length of the string. For alternating characters, such as 10, each segment is of length 1, and the result is also 1. Finally, an empty string is addressed during input validation, ensuring the algorithm behaves predictably for all possible inputs. This solution determines whether the longest contiguous segment of ones in the binary string is greater than the longest contiguous segment of zeros. It uses a single pass (O(n) approach to maintain the counts of current and maximum streaks for both ones and zeros. The variables max_ones and max_zeros keep track of the maximum lengths encountered so far for sequences of ones and zeros, respectively. Similarly, current_ones and current_zeros track the lengths of the currently active streaks. The loop iterates through each character in the string. If the character is 1, we increment current_ones and reset current_zeros to 0, as the streak of zeros is interrupted. Conversely, if the character is 0, we increment current_zeros and reset current_ones. After updating the current streak, the code updates max_ones and max_zeros by comparing them with the respective current streaks, ensuring that the maximum lengths are always up to date. Finally, the function returns true if the longest contiguous segment of ones is greater than the longest contiguous segment of zeros, and false otherwise. This solution handles edge cases such as strings with only ones, only zeros, or alternating characters efficiently. Here, we have the Java implementation of the solution. The method check0ones takes a string s as input and determines whether the longest contiguous segment of ones is longer than the longest contiguous segment of zeros. To do this, we use 4 variables, maxins and max_zeros, to store the maximum lengths of contiguous ones and zeros encountered so far, and current ones and current zeros to keep track of the lengths of the current segments as we iterate through the string. Inside the loop, we check each character in the string. If the character is 1, we increment current ones and reset current zeros to 0 since the segment of zeros has been interrupted. Similarly, if the character is 0, we increment current zeros and reset current ones. After updating these counts, we calculate the maximum values for maxins and max_zeros using the math.max function. Finally, the method returns true if maxins is greater than max_zeros, and false otherwise. Now, in the main method, we test the solution with several examples. The first test case, 1101, outputs true because the longest segment of ones has a length of 2, while the longest segment of zeros has a length of 1. In the second test case, 111000, the output is false since both segments have equal lengths of 3, and the condition is not satisfied. Lastly, for the input 11010010, the output is false because the longest segment of ones is of length 2, while the longest segment of zeros is of length 3. These examples help verify that the implementation correctly identifies whether the longest contiguous segment of ones is longer than the longest segment of zeros. To solve this problem, we start by initializing 4 variables, max_ones and max_zeros, to keep track of the longest contiguous segments of ones and zeros, and current_ones and current_zeros to track the lengths of the current segments as we iterate through the string. For the first character, which is 1, we increment current_ones to 1, reset current_zeros to 0 since the segment of zeros has ended, and then update max_ones to the maximum of its current value in current_ones, which is now 1. For the second character, also 1, we increment current_ones again, making it 2, reset current_zeros to 0, and update max_ones to the maximum of its current value in 2, resulting in max_ones being updated to 2. Next, when we encounter the third character, which is 0, we increment current_zeros to 1, reset current_ones to 0 since the segment of ones has ended, and update max_zeros to the maximum of its current value in current_zeros, which is now 1. For the fourth character, which is 1, we increment current_ones to 1, reset current_zeros to 0 as the segment of zeros has ended, but this time, max_ones remains unchanged at 2 because it is already greater than current_ones. To determine the result, we compare max_ones, which is 2, with max_zeros, which is 1. Since max_ones is greater, we return true. Now let's examine a new example where the input string is 000111. We begin by initializing the same four variables, max_ones, max_zeros, current_ones, and current_zeros, all set to 0. For the first three characters, which are all 0, we increment current_zeros with each character, reaching values of 1, 2, and finally 3. After each increment, we reset current_ones to 0 and update max_zeros to the maximum of its current value in current_zeros, resulting in max_zeros being updated step by step to 1, then 2, and finally 3. For the last three characters, which are all 1, we follow the same process but for ones instead. We increment current_ones to 1, then 2, and finally 3, reset current_zeros to 0 after each increment, and update max_ones step by step to 1, then 2, and finally 3. After processing the entire string 000111, we compare max_ones and max_zeros. Both are equal to 3, so the function returns false. Now consider the input 101010, which alternates between ones and zeros. As before, we initialize all four variables to 0. For each character, we increment either current_ones or current_zeros depending on whether the character is 1 or 0, reset the other counter to 0, and update the corresponding maximum variable. However, since the pattern alternates, neither current_ones nor current_zeros ever exceeds 1. This means max_ones and max_zeros both remain 1 throughout the iteration. At the end of the example 101010, we find that max_ones and max_zeros are both equal to 1, so the function returns false. To summarize the approach, we use two counters, current_ones and current_zeros, to track the lengths of contiguous segments of ones and zeros as we iterate through the string. We update the maximum lengths, max_ones and max_zeros, whenever we finish a segment. Finally, we compare max_ones and max_zeros to determine the result. This method ensures that we efficiently solve the problem in a single pass through the string. The time complexity of this solution is O(n), where n represents the length of the input string, s. This efficiency is achieved because the algorithm processes the string in a single traversal. During each iteration of the loop, which runs n times, the operations performed are constant time. Specifically, we check whether the current character is 1 or 0, update the relevant counter for either ones or zeros, reset the counter for the opposite character, and update the maximum values using the max function. Each of these individual steps takes O(1) time. Since all operations are constant time and occur within a single loop, the overall time complexity is simply n multiplied by O(1), resulting in O(n). This ensures that the solution scales linearly with the size of the input string. The space complexity of this solution is O(1), meaning that the algorithm uses a fixed amount of extra memory regardless of the size of the input string, s. This is achieved by utilizing only four integer variables, max_ones, max_zeros, current_ones, and current_zeros, to store intermediate results. These variables are sufficient to track the state of the computation without relying on additional data structures like arrays or lists. As a result, the memory usage does not grow with the length of the input. This constant auxiliary space requirement makes the solution highly efficient in terms of memory usage. To better understand the efficiency of this solution, we can compare it to a naive approach. In the naive method, we might generate all possible contiguous substrings of the input string and count the lengths of segments of ones and zeros. This would involve nested loops, leading to a time complexity of O(n squared), as for each starting position, we would iterate through all possible ending positions. Additionally, the substring extraction and processing would contribute further overhead. The space complexity of the naive approach would also be higher due to the storage of these substrings. In contrast, the current solution avoids these inefficiencies by using a single traversal and constant auxiliary memory, achieving O(n) time an O(1) space. When considering best, average, and worst cases, the time complexity remains O(n) in all scenarios. For example, in the best case, where the input string is uniform, such as all ones or all zeros, the loop still processes each character once. Similarly, for a random string or one that alternates between 1 and 0, the algorithm processes every character in O(n) time. The efficiency of this algorithm can also be understood mathematically. Since the string is traversed once, each character contributes O(1) work. Operations like updating counters or evaluating the max function occur in constant time, and there are no nested loops or recursive calls that would increase the complexity. This ensures that the total work done is n times O(1), leading to a time complexity of O(n). Additionally, the algorithm's space usage remains constant, as it only relies on a fixed number of variables. In summary, this approach is optimal for the problem, providing linear time complexity and constant space complexity, making it highly efficient for even large input sizes. When solving this problem, there are a few common mistakes to watch out for. First, failing to consider edge cases can cause issues. For example, if the string contains only ones or only zeros, the logic might break because it assumes there's at least one segment of each type. This can lead to runtime errors or incorrect results. Another mistake is off-by-one errors, such as skipping the final segment because the loop stops before processing the last character in the string. This would leave out important calculations. There's also the risk of confusing the logic for identifying segments of ones and zeros, which can lead to miscalculations of segment lengths and ultimately incorrect results. Lastly, be mindful of inefficient repeated calculations, like recomputing segment lengths for overlapping parts of the string. This unnecessarily increases the time complexity, especially for long strings, and can be avoided with better optimization. A significant issue to address is space optimization. For example, storing all segment lengths in a list can unnecessarily consume memory, especially with large inputs. Instead, maintaining just the maximum length dynamically is more memory efficient. Now, let's look at some interview insights. Recognizing patterns of contiguous segments in binary strings is a key skill, and interviewers might test your ability to adapt the problem, such as flipping ones to zeros or identifying alternating patterns. It's good practice to start with a simple brute force approach to clarify your thought process, then transition to an optimized solution that uses constant space and a single pass. Don't forget to proactively highlight edge cases during interviews, like strings that are empty, contain only ones or zeros, or alternate between characters. Lastly, if asked about alternative approaches, such as prefix sums, discuss their trade-offs, explaining when they're helpful and when they might introduce unnecessary complexity. Understanding related problems can provide valuable context for this challenge. For instance, LeetCode 485 focuses on finding the maximum consecutive ones, while LeetCode 1004 and 487 explore variations of this problem with specific constraints, like allowing a limited number of flips. LeetCode 696 takes this further by counting binary substrings, which is a different but related way of analyzing contiguous segments. When it comes to alternative approaches, the sliding window technique is a popular choice. It's particularly effective for identifying ranges of interest within a string, and while it works well here, it might be overkill for simple segment calculations. This method operates in O(n) time with O(1) space, making it efficient, but you should evaluate whether its complexity is justified for the problem's requirements. Another option is the prefix sum approach, which is excellent for range queries like flipping bits but introduces additional memory overhead due to the pre-computed sums, making it less ideal for straightforward tasks. Finally, the two-pointer technique is another approach worth considering, especially for problems involving contiguous subarrays. This method is efficient, with a time complexity of O(n) and space complexity of O(1), making it suitable for many scenarios. However, applying it to this problem can feel less intuitive unless extra constraints are introduced, such as limiting how segments are processed or analyzed. While it's a powerful tool for certain challenges, its utility here is context-dependent and may require additional logic to fully leverage its strengths. Ultimately, the choice of approach should balance simplicity, efficiency, and the specific requirements of the problem at hand. Great job! We've wrapped up our discussion on this problem. Remember the importance of building intuition with brute force solutions before optimizing. Keep challenging yourself with similar problems to improve. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!